Note 6.2, we're going to cover some more of our logs, and this time we're going to concentrate on solving those. We did a few exercises in our last lesson with expanding and simplifying, so we're going to pull out some of those little tricks and some of those log laws and see if we can solve for x. Okay? So first of all, you can see we've got this issue here with an x inside of the natural log here and inside of this one, and we can't just divide everything by ln. Okay, it just doesn't work that way. Okay, so let's apply a log law, and of course we can simplify this using that log law that says if I've got two logs added together, okay, I can combine them through multiplication. Okay. So, and I'm going to go ahead and distribute it in one step. This would be x times x, x squared minus 8x. And on the other side, we also have a log law here with the 2 on the outside as a coefficient. Our exponent log law says that we can take this and do the natural log of 3 squared, which of course is 9. So we've already applied 2 log laws, and then we can also even apply that log law that says if I have the natural log of something, say m, and the natural log of something n, then the only way these can be equal is if m equals n. So let's just take this inside here and set it equal to the inside over there. When we do that, we'll end up with x squared minus 8x equals 9. Subtract the 9 from both sides. X squared minus 8x minus 9 equals 0. And now we're right back to, you can see, a problem we saw way back in Algebra 1, and that is by, most likely, factoring this. And what does this factor to? Well, x minus 9 and x plus 1 will give us the negative 9 and the negative 8x, which means x will equal 9 and x will equal negative 1. Now, we do have an issue with this that we need to take care of, and that is the fact that one of these will not work in our equation up above. And that is, as you recall, we have domain issues when we deal with natural logs. In this case, in our first problem, our first part of the problem, this x has to be greater than 0. This is not greater than 0. If we want to check on the second expression in this, the x minus 8 also has to be greater than 0, which means x has to be greater than 8. And of course, 9 is greater than 8, so we are okay with that. Okay? When we deal with these, remember what we did with our domain issues in the past, and that is we choose the domain that is the most restrictive, and this one is the most restrictive because it excludes all those numbers from 0 to 8 that weren't excluded from this one. So our final answer is x equals 9, and if you want to substitute it in to check it out, I think you'll find that it does work out. Let's take a look at our next one. In the next one, we have 2 exponents, and in the past, we just were able to get those out of there by getting like bases. But there's no way we're going to get a 5 and a 3 to be a like base. We can't square something or cube something and get 5 and 3. Okay? So a new set of dilemma that we can do. Okay? Which means we'll go back to that idea that if we take the natural log of both of these, we can do that. It's part of the properties of equality that we can take the natural log of both sides. And when we do that, now we'll apply that exponent rule in reverse that we had over here. And that is that these exponents on the inside can now come out and give us x minus 2 as the coefficient, and the natural log of 5 would have to equal x as the coefficient times the natural log of 3. Let's go ahead and distribute this natural log of 5 to get x times the natural log of 5 minus 2 times the natural log of 5 equals x times the natural log of 3. Now we need to decide which side do we want to put the x's on, and I think I'm going to subtract x times the natural log of 3 from both sides, and while we're at it, let's go ahead and add 2 times the natural log of 5 to both sides. What are we going to be left with? Well, this will be x times the natural log of 5 minus x times, oops, that should be a 3 in there, I think, the natural log of 3 equals, on the other side over here, 2 times the natural log of 5. We can just factor out the x. This would be x times whatever the natural log of 5 is minus the natural log of 3. And let's go ahead and use our exponent rule here and change this to the natural log of 25. Love this stuff. And then, of course, to solve for x, all we have to do is take the natural log of 25 and divide that by the natural log of 5 minus the natural log of 3. And I think we'll stick with that. Next one, same dilemma. Trying to get like bases won't work. So we're going to have to do the natural log, which means 2x minus 1 times the natural log of 3 will equal the natural log of 7. And you can see this time I kind of skipped this step here because I know why I'm taking the natural log of both sides to get this 2x minus 1 as the coefficient. This time I'm not going to distribute this because I think it's easier if I just divide both sides by the natural log of 3 and leave us with 2x minus 1 equals the natural log of 7 divided by the natural log of 3. Two steps left in our algebra from here. Add 1 to both sides and then divide by 2. And we get something as crazy as this. The natural log of 7 divided by the natural log of 3. Remember, we added 1 to get rid of the 1. And then we're going to take this whole thing and divide that by 2. Whatever that is, that's our final answer. Next one. This time I can see in here that I do have some like bases in here that we can consider. So we know that 4 would be 2 squared. That's raised to the x power minus 2x minus 12 equals 0. From here, a couple different ways we can solve this. But what I want to do is consider this as, remember, power to a power multiply. So I could write this as 2 to the x, all of that squared. So now I've got this thing here, 2 to the x, and I'm squaring that. And then what I'm going to think of is I've got minus 2 to the x minus 12 equals 0. Well, look at this. This is the same thing as that, 2 to the x. I've got it here and I've got it there. In other words, I've got one of these times that. Okay? So if you don't see it, this should look like something, and I'll use a different variable here. It should look like, say, a squared minus a minus 12 equals 0. Okay? This thing here being a. I've got one of them here and one of them here. This one happens to be squared. This one I'm just subtracting, which we know if we had a problem like this way back in Algebra 1, we would solve it by factoring. And we'd put the a here and the a there, and then we know that a negative 4 times a positive 3 would give us 12, and a negative 4a plus 3a would give us the negative a. So let's do the exact same thing over here, and let's write it like this. 2 to the x times 2 to the x. That's what our a value is. And then minus 4 and plus 3. The negative 4 times the positive 3 will give us the negative 12. And the negative 4x times the, negative 4 times the 2 to the x plus the 3 times 2 to the x will give us the negative 1, 2 to the x. And again, now we're back to solving these by setting both of these equal to 0. So in this case, we would set this equal to 0, and this would give us 2 to the x equals 4, or 2 to the x equals negative 3. And I think you can easily see this. X has to be what? 2 to what power is 4? 2. X equals 2. Oops, got a problem on this one. Can 2 to the x ever equal a negative number? No. If you got a positive base, you can never get a negative number out of just an exponent. So not here, and yes here. X equals 2. Let's do a few more like these. Okay. First one, very similar to the one we just did. The trick here is recognizing that 9 to the x can be written as 3 squared to the x, or 3x quantity squared, or 3 to the x quantity squared. So let's go ahead and use that right here and write this as 3x quantity squared minus 5 times 3 to the x, and then plus 6 equals 0. Why do we write it like that? Because now we can see that this is a second degree trinomial that we can usually solve by factoring. If we can't factor, we might have to use the quadratic equation or quadratic formula, or we could even graph it. But in this case, let's see if this factors. This would be 3 to the x and 3 to the x in our two binomials. And then we need a positive 6 here. But the middle term is negative. Only way we can do that is if both of these are negative. And what times what will give us 6, but when we add it together, we'll get a negative 5. What do you think, Dana? What times what is 6? Add it together, we get 5. Yes. So this would be a 3 and a 2. And then we're just going to solve these, knowing that 3 to the x would have to equal 3, and 3 to the x would have to equal 2 if either one of those are equal to 0. First one's real simple to see. Only way we can do this is, of course, when x equals 1. But the next one is going to require us to use our log laws again. And that is that x times the natural log of 3 would have to equal the natural log of 2, our exponent rule there. Solving, this would be the natural log of 3 divided by the natural log of 2 will equal x. And we actually have two solutions to this one. One's simple one, x equals 1, and one, it's going to give us a really weird number. All right, next one, falling into, again, a case where we can't get like bases out of this. So we'll take the natural log of both sides to get those exponents as coefficients. This time I have an x here and an x here, so I will not be able to just divide, or excuse me, just divide by the natural log of 2. I need to combine the x terms, so we're going to have to distribute and get x times the natural log of 2 plus 4 times the natural log of 2 equals x times the natural log of 7. This time I'm going to keep this 4 natural log of 2 on the left hand side and subtract this x times the natural log of 2 from both sides. X times the natural log of 7 minus x times the natural log of 2 would be 4 times the natural log of 2 equals x times the natural log of 7 minus the natural log of 2 by factoring out the x. And then I think we have it. 4 times the natural log of 2 divided by the quantity of the natural log of 7 minus the natural log of 2 equals x. Final answer. Let's continue on with our next one. No like bases. Okay, if this were 27, okay, I'd write it as 3 cubed. I'd get like bases, set my exponents together. But no matter how I try, I can't use that in this case. So we're using the skills we learned in this chapter, and that is that 3x minus or plus 2 comes down as the coefficient when we take the natural log of both sides and then use our power rule. This time there is no x on the right hand side, so we'll quickly do one algebra step, dividing both sides by the natural log of 2. And then again, solving this, we can have 3x equals the natural log of 3 divided by the natural log of 2 minus 2. And then dividing all this by 3, we'll have the natural log of 3 divided by the natural log of 2 minus 2, all divided by 3, or, hey, let's just multiply by 1/3 since I'm running out of room. Right, our next one involves that natural log with terms, the x inside of each one of these terms. So it's going to be similar to what we did on the very first example of today. And that is, let's use those log laws as best we can and rewrite the left-hand side as the natural log of the quantity of x minus 1 times the quantity of x plus 2, and that equals the natural log of the quantity of x minus 3 squared. Now, since both of these are inside of a natural log, we're going to set both of those equal to each other, and we can just forget the natural logs. We're not dividing by the natural log. Okay? We're just saying, hey, the inside of these have to be equal to each other. And that will be the case. Then let's go ahead and FOIL this one, and the same thing over here. This, of course, will be an x squared. A plus 2x minus x will give us a plus x, and then, of course, a negative 1 times the 2 will give us a negative 2. On the other side, we'll have an x squared, and remember, this will be a negative 3x. Negative 3x will give us a negative 6x, and, of course, negative 3 times negative 3 is a positive 9. That was a difference of squares. Oh, I like this because I can subtract the x squared from both sides real fast, and then add the 6x to both sides. While we're at it, let's just add 2 to both sides and clean everything up. That should leave us with 7x equals 11, or x equals 11/7. Now, hopefully we learned our lesson from the first one, and that is, hey, we have to check domain on this. So before we circle this and say that's our answer, let's look at each one of these and see if this works out for us. Okay? So first of all, in this one, the x minus 1 has to be greater than 0. Remember, the natural log graph looks like this. Okay? And the inputs, the x's, have to be greater than 0. So this inside has to be greater than 0, which means x has to be greater than 1. Obviously, 11/7 is greater than 1. Oop, checks out okay here. Let's check the next one. In this case, the x plus 2 has to be greater than 0. Subtracting 2 from both sides, and x would have to be greater than negative 2. Of course, we've got a positive number. It works out perfectly there. Let's check on the right-hand side. In this one, the x minus 3 has to be greater than 0. Add 3 to both sides, and x has to, oops, I don't think 11/7 is greater than 3. We'd have to have more than 21/7 to be greater than 3. And in this case, with this as our domain, this does not work. So in other words, this is a no solution. So again, use your log laws, turn it into an Algebra 1 problem, solve it, but before you say, yep, this is my answer, check. And in this case, we have to check in 3 different spots for domains and make sure this passes the most restrictive of these. Okay. Let's take a look at the next set of problems. Okay. When am I ever going to use this? Well, there is something called Newton's law, and yes, it's the same Newton who had the apple fall on his head. He was into more things than just gravity, and this equation relating how things cool, or really it could be heated up. It doesn't matter which one, but we just generally call it Newton's law of cooling. Works like this. The temperature U of a heated object, so this is U, at a given time, so U of t, can be modeled by this function. And you can see in this function that the variable, the independent variable t, there's a lot going on in here. That independent variable actually is right over here in the exponent, and we have that weird number e in here also. So here's what it is. What we assume is T is the constant temperature of the surrounding medium. Okay, so it could be just taken out and put in room temperature. It could be in a refrigerator. It could be in a heater. It could be in a water bath. Okay, so what is assumed on this is that temperature T is constant. It doesn't go up or down. We're keeping the refrigerator at the same temperature. We're keeping the room at the same temperature. Okay? And next, this one right here, this U of t, or excuse me, U sub 0, is the initial temperature of the object. So how warm or how cold was the milk when you put it in the refrigerator? How hot was the coffee when you pulled it out of the microwave? Okay, something like that. And then something that is unique to each situation is this constant K. Okay, and K will be negative when something is cooling. Of course, it'll be positive if something's being heated up. Okay, so let's take a look at a few of these problems. Okay, or I guess just one of these problems. An object is heated to 100 degrees, and let me make a note. If there is one on a test or a quiz, this equation will be given to you. You do not have to memorize this. Okay? But of course, on the homework, it may not write that equation out. You may have to go back to your notes to find it. So here's what we have. We have an object that is heated to 100 degrees Celsius. Okay? In other words, this is our U sub 0, that initial temperature of the object. We've heated it up, and now it's put in a room to cool, and the temperature of that room is 30 degrees. And again, we're assuming that it stays 30. It's not like in the Ross High School where sometimes it might be 75 degrees and then it's going to drop 3 blocks later down to 50 degrees. Okay, it's going to stay there. Okay, so this is our capital T in the equation, and that equals 30 degrees. And these are all in Celsius. Now it says if the temperature of the object is 80 degrees after 5 minutes, then when will its temperature be 50 degrees? Now, what I'm going to ask you to do is, on these, just to keep track of what we have and what we know, is just put a little T table with lowercase t being the temperature, and, oops, don't need that, the U of t, the temperature of the object, as the x and y. Okay? So first of all, when it says the object is heated up to this and then allowed to cool, that gives us the initial temperature when time is 0. So as soon as it comes out, it's going to start cooling. So we're going to say T equals 0, not 1, but at 0 time, we have this. Next, in the problem, it says at 5 minutes, we're down to 80, and then it says when will its temperature be 50? So we're solving for T here. Okay. I'll just put it as T1, the temperature that we're looking for, so not to confuse it in our equation. Okay? So let's go back up here to the equation, and let's start filling in some things on this. Okay? this says the temperature of the object at any time, U of t, will equal capital T, that's the temperature of the surroundings, which is 30, plus...
Good morning. At this time, we need all students going on the Earth Science field trip to make their way to the cafeteria. Again, all students going on the Earth Science field trip, please make your way to the cafeteria now. Thank you.
Great. So, this here, U sub 0, is this one right here. That's the 100 minus, in this correct case, the surrounding temperature, which is 30, times E, and we don't know what K is, to the T. Okay. This variable here, we need to solve before we can get to this one here, this T, when the temperature is 50. That's why in each one of these problems, they also give you another condition, and that's this condition right here. We're going to use this set of values, substitute those in to solve for K. So this says at t equals 5, U of t will be 80, and of course this will be a 30 plus, and then we should be able to do this in our head. 100 minus 30 gives us 70. E to the K, what we're looking for, times T, which is 5. Subtract the 30 from both sides, we get 50 equals 70. E to the K times 5, or 5K, I probably should have written it like that. Dividing both sides by 70, we'll get 50 divided by 70 equals E to the 5K. Then, of course, you can see why this is in this unit, because we've got K as an exponent. How are we going to get that out of the exponent? We're going to take the natural log of both sides. So what's that going to look like? This will be the natural log of 50/70ths, which of course I'm going to simplify to 5/7 equals 5K times the natural log of E. And again, I just skipped that step there because I know why I'm taking the natural log of both sides, so that this exponent can come out as the coefficient. And we got a little gift here because the natural log of E is 1. So we can solve for K by dividing both sides by 5 and write K equals the natural log of 5/7, close your parentheses on your calculator, and then divide all of that by 5. So now we're ready to solve for t when U of t equals 50. In other words, 50 equals the 30 plus, remember this here is 70, 100 minus 30, and that's going to be E, and then that K value, this right here, since I'm a little cramped for space, I'm just going to write it like this and do a quick little arrow over there to say, hey, that's what's right here, to the T. Some of the same steps we just did over here to solve for K, we're going to do to solve for T. And that is to subtract 30 from both sides. This will give us 20 equals 70 E to that, again, I'm going to just put it in parentheses since I'm really cramped on space. Divide both sides by 70, and this will be 20/70ths equals E to that same K times T. Take the natural log of both sides, and we'll get the natural log of 2/7 equals that K value times T. So where can I go from here? This is going to be t equals the natural log of 2/7 all divided by this thing right here, the natural log of 5/7, that divided by 5. I won't take time to put that in the calculator, but you hopefully will be careful because there's a lot of parentheses going on in this. Or t, and I guess since I called it t1 up there, I probably should have been going t1 each time. Our t is going to equal, when I put it in the calculator, it's going to be approximately 18.616 minutes. So just under 19 minutes for that object to cool from 100 degrees to 50 degrees. Next, it says, hey, let's find the temperature when the time is 20 minutes and 10 minutes. So in this case, it's just going to be a U of 10 and a U of 20, which would be 30 plus 70 e to the natural log of 5/7 divided by 5 times 10, and 30 plus 70 e to the natural log of 5/7 divided by 5 times 20. We can put that in our calculator if we want to. I think I will. It. And I think I'm going to go ahead and put this in the y equals, clear this out, and put it in as 30 plus 70, and then e to the, and again, I want to put this in here so you can see how many parentheses that we have. First of all, it'll be the natural log of 5 divided by 7, close that parentheses. That gets divided by 5, and then all of that gets multiplied by x. And then close the parentheses on that, clear this out, and I'm just going to jump to our table and clear out some of these. Oops, go to. All right, go to. I'm messing things up here. All right, I'm just going to go up here and put in 10. 20 is already listed in there, and you can see that our answers are going to be in the first one. This would be approximately 65.714 degrees. After 20 minutes, it's going to be 48.222. So at almost 19 minutes, we were at 50. And then from here to 20 minutes, we didn't even lose 2 more degrees. And then it says, is the rate of cooling linear? Or constant, I'm sorry. Is the cooling rate constant? Okay. And I think most of you should know that sure doesn't look like a constant rate here, because you can see in our first one we went from let's just do a quick little slope calculation here between the first set, from 0 when we were at 100 to 5 minutes when we were at 80. Let's do the slope of that one. Slope 1 would be 100 minus 80 divided by 0 minus 5. This is going to give us a negative number here. Okay. 20 divided by negative 5 gives us a negative 4 slope. And then let's just use from 50 or 5 minutes when we were 80 degrees to which one you want to choose? The 18, the 10, or the 20? Which one you want to use? Let's use the 10. At 10 minutes, we were at 65.714. So let's calculate the slope there. M2 equals 80 minus 65.714, all divided by 5 minus 10. Let's just put a little, let's just do it in our head because we're just comparing. Oops, sorry. Had that off the screen. Again, 5 and 80, 10, and the 65 degrees. And again, I'm just going to do a quick little rounding because 65.714, I'll just round to 65. 80 minus 65 is 15. Of course, 5 minus 10 is negative 5. And this would be telling us that the slope between 5 and 10 minutes is actually about 3 degrees. So in the first 5 minutes, it's averaging losing 4 degrees every minute. But in the next one, it's only losing 3 degrees. And you kind of think of that in real life, how things start to cool rather quickly, but then as they kind of get close to each other, their rate just kind of slows down and it takes a little bit longer for them. Okay? That's why when you put things on the stove and you turn the heat way up on it at the beginning, okay, the heat rises really fast, and then you can, oh, wait a second, don't want to burn this, you can turn it back down, and then it's going to kind of level itself out. Okay? So, Newton's law of cooling problem, using a little bit of natural logs in there to solve it. Okay. Now, we're going to conclude this lesson by talking about something called a logistics curve. What in the world is a logistics curve? Well, a logistic curve is something that's necessary to take one of these exponential growth curves and make it more realistic. Okay? So for example, if we start putting bacteria in a petri dish, all of a sudden that bacteria starts growing, right? And then this one grows another one, and another one, and another one. Okay? And they actually multiply. They're not linear. They start getting bigger, 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 bigger. Now, did that bacteria eventually take over the world and now cover the whole world? No. Okay? It had to level out. It didn't just keep growing and growing and growing and growing and growing. Okay? So, in reality, things that follow a logistics curve, in other words, population, spread of disease, spread of rumors, okay, they follow something that looks like this. Okay? So, for example, I was just talking to Mr. Martin, and you know what? He did a couple surveys of students, and he found out that, hey, we're just getting a little bit worn out, and he is going to recommend that we're actually going to start spring break next week, and we'll take off after Good Friday, and we'll take that next week off, and we'll have 2 weeks of spring break. Okay, what do you guys think of that? Is that a good idea? Okay, now if I told you guys, hey, keep that to yourself, would you keep it to yourself? No. You'd be all over the place, right? If you had your phones right now, what would you be doing? I said, hey, I just found out this secret. What would you guys do? Tell one person? Right, you check the group chat, okay? So boom, we get this rise, okay? Right now, there's only 7 of us in here. It's going to start down here. But of course, 7 you are going to tell probably 5 people. Are those 5 people going to tell another 5 or 6? Okay, so you can see where this starts going up just like this, like this, like this. Okay, But by the end of this block, when the bell rings and you start going through the hallway, hey, did you hear about? What are they going to say? Yeah. Oh, no, I didn't hear that. You're going to have a few that said, hadn't heard it. But won't we reach this point where, yeah, I already knew that. I heard that. Okay? Jay told me that. Oh, no. Sam told me this. Okay? And you may not find some people. So in other words, it's still going to be growing the number of people, but it's not going to be growing so fast. And as a matter of fact, it's got to reach a point where everybody knows the rumor, right? Won't it have to reach a maximum value? That maximum value is called the carrying capacity. Okay? In our case, it would be the actual number of students in the building, say 990. Okay? So when we reach that, there is nobody to learn the rumor. Everybody knows. We've reached our carrying capacity. We've maxed out. Okay? That is C, our carrying capacity. And this equation, if we were to, this graph, if we were to write an equation of it, it would be something that looks like this. It still has an E in here to a power with the time on it, okay? But eventually it's going to level out. In this, we have a fancy word called inflection point. Inflection point. And you can probably see it anytime, not probably, you can easily see it when you look at any one of these graphs. And you can see that's where it kind of does the happy parabola type shape to the sad parabola type shape. It kind of changes shape. This right here is called the inflection point, where it changes from being what we call concave up to concave down. Okay? And the cool thing about this is, if the carrying capacity is 100, this is going to be 50. If the carrying capacity is 1,000, this will be 500. This is always 1/2 of the carrying capacity. So, let's take a look at an example here. And in this example, it says that we've got a bunch of fruit flies in a closed bottle with bananas. Okay? Now we know, of course, that those fruit flies are going to do what fruit flies do, and they're going to multiply, right? Okay? So this equation will be a logistic equation. We will reach the point where there will be no way we can get any more fruit flies in there, just because of maybe the food, the oxygen, whatever, or it may be just the plain space in there. Okay? So, first of all, it says, what is the carrying capacity of this? Okay? In other words, when will this reach its maximum amount? Okay? Now, what I want you to think of real quickly on this is if I just look at this denominator here. Okay? If I look at that denominator closely, that denominator is 1 plus 56.5 e to the negative 0.37 t. So, as t gets bigger and bigger and bigger, this is to a negative exponent. So this is going to get smaller and smaller and smaller and smaller and smaller. Eventually, this is going to get so small that this part right here is going to go to 0. 0 times 56.5 is 0, plus 1 is 1. So in other words, as t goes to infinity, gets bigger and bigger and bigger, this denominator, 1 plus 56.5 e to the negative 0.37 times t, all of that is going to go to 1, because this part right here goes to 0. Which means that as t gets bigger and bigger and bigger, this carrying capacity, the population, that population is going to go to C, the carrying capacity, which is going to equal 230. And look again, back to the equation up above, and you'll see that in the general equation, whatever is in the numerator, that is our carrying capacity. Okay. Next, it does ask for what is the growth rate? At what rate is this growing? And in the equation up here, that value of B, our growth rate, is equal to whatever that B value is. Okay? And we can say the absolute value of this since it's growing. And of course that is a negative 0.37, or a growth rate of 0.37, or 37%. Okay? It's growing 37% each time, or during each unit of time. Okay? What's the initial population of the fruit flies? Well, remember, when we have initial population, that's when t equals 0. Okay. So let's take a look at this equation. When t of 0, this will be 230, 1 plus 56.5 e to the negative 0.37 times 0. Negative 0.37 times 0 is 0. E to the 0 will be 1. So this will be 230 divided by 1 plus 56.5, or 57.5, which actually equals 4. There were only 4 fruit flies in there at the very beginning. Next, it says, let's find the population after 5 days. In other words, let's let t equal 5. P of 5 will equal 230, 1 plus 56.5 e to the negative 0.37 times 5. If we put that in our calculator, we'll get about 23 flies. So in 5 days, we went from 4 to 23. How long will it take to reach 200? Okay. Well, let's see what we get here. This is P of t, I'll put it 1, equals 200. We're trying to find that time. So this will be a 200 equals 230. 1 plus 56.5 e to the negative 0.37 times t1, and solving for that. Okay. What I'm going to do is bring this out by multiplying both sides by the denominator here, and while I'm doing that, I'll divide both sides by 200. The result will be 1 plus 56.5 e to the negative 0.37 t1 equals 230 divided by 200. 56.5 e to the negative 0.37 t1 equals 23 divided by 20 minus 1, subtracting that 1 from both sides and simplifying this just a little bit. Let's go ahead and write this as e to the negative 0.37 t1 equals this 23 divided by 20 minus 1. All of this gets divided by 56.5. And then we're going to take the natural log of both sides. That's going to leave us with, the e is going to go away because it's the natural log of e, and then this exponent becomes the coefficient, negative 0.37 t1 equals the natural log of 23 divided by 20 minus 1, all of that divided by 56.5, and then we'll take the natural log of that. And hopefully our calculator has good enough battery to put all this in there, because we're going to have to take the natural log of 23 divided by 20 minus 1, all divided by 56.5. And then take all of that and divide it by negative 0.37 to get our t. Fortunately, I was able to put that in the calculator ahead of time and got 16.030 days. 4 at the beginning, 5 days later we're at 23, and then in just over 16 days we'll have 200 flies flying all over those bananas. Sounds yummy. What is the inflection point? Okay, now here's the key word on this. It says inflection point, which means we're going to have an x and a y value. The easy part of this is knowing that our carrying capacity from the beginning was 230, so we have to just take half of 230, or 115 is our y value for this. So if we were looking at this graph, the curve would look like this. The carrying capacity of 230, we can't have more than that many flies, would be here, and half of that 115, and we just need to find this time here. And that's when we do 115 equals that 230 divided by the quantity of 1 plus 56.5 e to the negative 0.37 times t. And now I'm looking at saying, man, all that algebra I did over there, I should have just taken the time to put that in my calculator and found the intersection. And if we did, we would find that indeed this t is at 10.903 days. So almost 11 days will be when we reach half our carrying capacity, and the number of people, or the rate at which people are finding, or rate at which the fruit flies are reproducing is going to start slowing down. They're still going to be increasing in there, but not at such a higher rate as it was before. That is logistics. I knew you were waiting all year long to learn about logistics.